Okay, here goes on the next video then. Graph transformations. I'm going to split this into two videos. So this first video is just about our translations. If you remember the definition of a translation through your previous schooling, it's where a shape changes position but it doesn't actually change the size or the dimensions of the shape. So in terms of graphs, the shape of the graph is going to be the same, but the position on the axis is going to just change a bit. I'm going to introduce a bit of slightly different notation as well for this, so just make sure that we're up to speed with everything that we need to know. Okay, so first one is something like you get some kind of graph where your function of x, that's all f of x means, f of x, and what we do is we add some constant a onto that. Let's just have a look at a graph and see what happens. So I'm going to use a graph over here. If I just move over a second, okay. And here's a graph that I'm going to be dealing with today. We can see this graph here. It's just the graph of x squared, as you can see over here. It's a graph of x squared minus 6x minus 7, and it produces this nice quadratic that we're happy with. We're used to seeing quadratics. That's the sort of thing we'd expect. Now, let's just, on top of that, look what happens if we take our function of x and add something on. That's all this means. That's all this is saying to us here. We're taking our function of x, which in this case is x squared minus 6x minus 7, that's this graph, and then I'm going to add something onto the end. So it's outside the bracket, we add that constant on. So essentially what I mean by that, if we took our function of x, which I'll write out, we could say that, what have we got, x squared minus 6x minus 7. Outside of that, what I'm going to do is I'm going to add something on. And we called it a in the definition here. We called it a. I might define it as being something like, I don't know, plus 3. Now what effect is that going to have on the graph in terms of translating it? Well, let's have a look. I'll insert the translated graph over the top of this. And if we have a look, what we should notice is our original graph was the green quadratic, as you can see. The new graph is the blue one, and over here what's happening, let's look at some critical points. The original graph's here, this new one, the minimum point is up 3, and if we look at the intercept, it's the same thing. It's going up from that minus 7 up to minus 4, so it's moving up 3. So the effect of that, let's come out again, the effect of that really is when we add 3, we noticed it's shifted up 3. So if we add a to our function of x, it's just going to shift a vertical translation, we call it, or shift it up by whatever the value of a is. So let's just formalise that in our notes. In fact, what we should have is we should have this as y equals. Okay, so for f of x plus a, we say that this is a vertical translation. Am I going to write over it? Yeah. Translation of a. And you may have seen the translation idea when you did your previous schooling. Could be written in vector form. So we have our x shift on top and our y on the bottom. So this would be a shift of, in vector form, 0a. So that would be if we're doing it by vector notation. Okay, nice easy one to get us started with. Second one we need to think about, let's just move it down a bit. Second idea, number 2, is going to be our f of x plus a. Okay, now this is what often confuses a lot of people, but if we see the process through, we should see it working okay. Right. First of all then, what does this mean? F of x plus a. The way I like to think of it is, instead of the whole function of x, as was previously the case, previously the whole function of x, we added a onto the end. Instead of that, we're going inside the function now. We're going inside the function. To every x within that function, I'm going to add a. So let's just deal with this in terms of the same graph that we had just now. So if we start with y equals x squared minus 6x minus 7. If I'm going to add a to all of my x's within that function, what that would become is, in fact, I'm going to just change the notation. This is going to upset some of you for your notes. If our original equation, our original function was f of x equals this, then the f of x plus a should equal, well, I'm going to add a to every x. So wherever I see an x, instead of x, I'm going to write x plus a minus 6 lots of x plus a. You probably noticed that first one should have been squared. So then minus 7. So it's fundamentally the same function. We've still got something squared minus 6 lots of something minus 7. But instead of x, now wherever the x was, I've now got x plus a. So let's have a look at what happens to the graph now. I think what I'll do is I'll use the 3 again, and I'll use the same graph. So our original function is going to be like this, and I'm going to go over here to put it in. Our original function is going to be this graph, just like we used previously. We're starting with this x squared minus 6x minus 7. What I'm going to do to that is I'm going to do my function of x plus 3 within a bracket. So what would the f of x plus 3? Instead of a, now let's use a 3, so that should be x plus 3 squared minus 6 x plus 3, and then if I shift across a bit, minus 7 at the end. Okay, let's have a look at this graph too then, for which I'm going to go over here and lay it on top again. Okay, so this is what that would look like, x plus 3 squared minus 6 lots of x plus 3 minus 7. So let's have a look at what's happening here. Again, let's look at some critical points. Minimum point down here on the original graph, this green one. Now what's happened, it's moved across, it's moved down 3. Again, our y-intercept, it's moved across, it's moved down 3. Instead of moving up 3, like we might expect, it's actually moved kind of the counterintuitive way. And let's just think about, we can think about in terms of our table of values why that's happening. So I'm going to just move slightly further over here, and we're going to think about our table of values. And I'm only going to do 1 or 2 values so we can see what I mean. So we had a nice green for our original equation. That was y equals x squared minus 6x minus 7. So let's just look at what the table of values look like. And I'm just going to do this for x being values of 0, 1, and 2. Okay, so what value would we get for y for the first one? Well, if we plugged 0 into here, this would become 0, this would become 0, so our y value of that first one is going to be minus 7. You have to think about 1 a little bit. So when I plug 1 into here, I'm going to do 1 squared, which I know is 1, minus 6 lots of 1. So 1 minus 6, that's going to be minus 5. Take away another 7, that's going to become minus 12. So I can put in there minus 12. And then substituting in value for 2. 2 squared I know is 4. Now I'm going to take away 6 lots of 2. So it's 4 minus 12. So that should be minus 8. Take away another 7, that should be minus 15. So that should be minus 15. Okay. Let's just check quickly I've got my values right. For the green one we should have 0, minus 7, cool, that works. 1 I got as minus 12, and 2 I got as minus 15. Fantastic, I managed to get my maths right. Okay, getting better with my numbers. Let's just see what happens now with that blue graph with the table of values, and it should give us a sense of why this shift's happening in the wrong direction. Okay, now we're going to have a go at y equals what was it, x minus 3 all squared, minus 6 lots of x minus 3, and then minus 7. Okay, and I'm going to choose to do this for a few slightly different values, and x being, what do I want it to be? X being 2, 3 and 4, and then we'll work out what the y is. Okay, so just like before, let's plug my value for x into here. Well, the value of x being 2 is now going to be, we're going to subtract 3 from it. So in effect, this is going to be acting like minus 1, because 2 minus 3 is minus 1. So minus 1 squared gives me 1. Take away 6 lots of minus 1. That's going to actually add on. So I was at 1 plus 6 is 7. Take away another 7. That's going to become 0. Okay, what happens for 3? And hopefully you're spotting why I'm doing this already. What happens for 3? I'll plug 3 into my value here for x. 3 minus 3 becomes 0. Wonderful, 0 squared. 3 minus 3 becomes 0, so this whole thing's 0. My answer is just going to be this, minus 7. And then finally for 4, what happens within each bracket? This x minus 3 becomes 4 minus 3, which is 1, so 1 squared, minus 6 lots of 4 minus 3, 6 lots of 1, which is obviously 6, so 1 minus 6, take away 7, that should be our minus 12. Okay, hopefully you've spotted why I've chosen these values. What's happening here is the x value 4 is acting like the x value 1 did here. The x value 3 here is acting like the x value 0 did here. And if we look at our graphs, it's exactly what we'd expect to happen. On our original graph, where we had the value of, what was I just referring to? Okay, on our translated graph then, let's go for that one. This value for 0, in fact 1. This is what I'm looking at here. The x value of 1, and that's how I know I'm looking at here. The y value is minus 15. Okay, that's acting exactly like the x value did for 3 up here. So that's why it shifts to the left instead of to the right, which might be quite intuitive. So if we look at our definition, I've zoomed out a bit, haven't I? Okay, so in terms of f of x plus a, this original thing that I was referring to, oops, got my rubber on. I'm looking here at my original f of x plus a. To get from f of x to the f of x plus a, that is a horizontal translation of minus a. Because remember here, what we did was we added on 3, and we found it shifted 3 to the left, or down my number line, down 3. So we've got a function of x plus a represents a horizontal translation. Horizontal translation. Need more space. Horizontal translation of minus a. So if I was going to write this in a vector form, vector notation, to get your transformation from f of x to f of x plus a, that would become, in my vector form, we'd move in the x direction minus a, and obviously in the y direction nothing. So that's what this would be as our answer. That's how we're going to describe it. And that's our first two transformations that we're dealing with. Now, it's quite nice to have a little recap. What's happened? Okay, well, both of my functions, both my examples here, what I did was, all I was doing was I was adding something on. It's just to notice the difference, whether we're adding a on after the function or adding a to the x's within the function. But whenever we add, we're always going to end up with a translation. Both instances as a translation, which remember meant that it's changing position on the axis, but not changing shape. And what we need to remember is when we change from a function of x to a function of x plus a, That's going to be a vertical translation of a, which is 0a, and from a function of x to fx plus a, we get a horizontal translation of minus a. That's the thing that everyone finds quite counterintuitive or forgets, which would be represented as vector notation as minus a over 0. Okay, now we're going to do some stretching and stuff for the next video, so I will see you there on the start of the next video.